is we need to talk about the exam, right? We talked about this on Wednesday. We want to set that. And the best dates that I think would be, we said like the 23rd, the 26th, 28th, or the 30th. You know, so I have, I don't know what it's called. It's called Experience ISU. And as chair, I'm supposed to be the one running it. And it bumps up right on the 30th during class time. If we had an exam during that time, then that would alleviate me having to record a lecture or something for you guys. I would do my best to make sure that the test is fairly straightforward. And of course, if there is any questions on the exam and I'm not here, you can write down assumptions and so forth, and always take that into consideration. Would anyone have any grief if we schedule?
I think it's fine.
Third is fine? Okay, those online, any discussion, comments, complaints, snide comments or otherwise? Keep them clean.
Dr. Savage, are we talking about the 30th?
Yes.
Okay.
The 30th of October, so 2 weeks from today.
I think we're good with that.
Okay. All right, hearing no complaints, it will be the 30th then. Okay.
And will that cover pumps too?
It will cover pumps, yes. We will be through pumps by then. And we may even actually incorporate pumps back into pipe networks by that time. All right, so given that, let's talk a little bit about pumps. We looked at different types of pumps, what they're able to do. Okay. Is that too annoying, that background image there? You guys can't see it on that one. On that one, you can see it a little bit. But... So pumps. We can have positive displacement pumps. And positive displacement pumps, as we talked about on Wednesday, these are pumps that are physically moving a volume of water or volume of fluid. Whether that is in an open system or a closed system. A closed system would be like a screw that has a pipe around it, or gears that are moving, and an open system would be like a fan or a, you could even consider almost a boat impeller. Well, that's, you can argue over that too, but a boat impeller is actually moving fluid, whereas a plane propeller is creating a pressure differential. So there's slight differences in those, but you could almost consider those the same thing. But like a fan in a room that's moving air, that's pushing a positive volume of fluid in a given direction. And so positive displacements generally do not care about pressure so much unless you reach a maximum pressure and they can no longer push. They push the same volume every time as long as it's within their system capabilities. And civils use these all the time for like water treatment. If we're putting fluoride in the system or chlorine in the system, we want to meter out a certain volume of the fluid. And so those are fairly easy. You just hook them up to the system, set them for the volume that you want, or connect it to your computer system, and it works great. The other type that we talked about was the radial pumps. radial or centrifugal. Okay, and I should be a little careful with this term radial because it actually has a dual meaning to it. We can actually classify a sub portion of these pumps by radial. And so let me show you a little picture here. Well, this is rather interesting. So I finally got the book, and in fact, they sent me 2 books now. I didn't get the original one, and then complained, and I said, send me an electronic copy. They didn't, and all of a sudden 2 books show up, and I see that they've changed. What is chapter 12 in the old book is now chapter 11 in this new book, which makes me interested. I told you to read 12, yeah, because I was basing that on the old one. What's that?
There's a while back, there's another one you told us to read.
Oh, and it was different?
Yeah.
Oh, well, I apologize. I thought the chapters were the same thing. And like I haven't even taken the time to pop this open. I just grabbed it today and I said, okay, we're going to talk about this. So it's chapter 11. So my apologies. We are on chapter 11 now. It's called Distribution Systems. And let me zoom in right here. Okay, so there is a figure in here. And this is 11.2.25. Pump efficiency is related to the specific speed and discharge. So this is a little bit difficult to understand, but radial flow is like a disc that has these curved veins into it, and the water comes into the middle, and the vein is like an arm that swings the fluid, except for it's actually curved this way. So if it's rotating this way, it flings the fluid, and the farther you get out on that curve, the more rotational velocity you have, because there's a bigger lever arm, right? And so it imparts a large amount of velocity to the fluid. And then if you come over here, you have a propeller then. Once again, this would be like your plane, or and I think I call the boat an impeller, but it's actually it's an impeller if it's inside, it's a propeller if it's outside, all right? But so we can actually have propellers inside of pumps as well, and those we call axial flow. And those are almost, oh, I'm sorry. Let me zoom back out here a little bit. Thank you for melting that. I really need like a screen in front of me so I can see what's on there. But all these radial mixed and propellers are still centrifugal type pumps, all right? And we're going to talk about the characteristics of a centrifugal pump, but I want you to know how to pick which type of centrifugal. So underneath this right here, I could put specifically radial, mixed, and I would call it axial. Okay, rather than propeller. I like axial better. All right, so this is pretty easy. There's something called the specific speed, and it's down on the bottom of this page. Let me see if I can bring it up here. I'm not going to go through the derivation of this just yet, because we will get to this when we talk about the similarity laws, but specific speed is fairly simple. So equation 11.2.7, the specific speed noted as N sub S is what we call the coefficients of Q to 1/2, coefficient of H to 3/4, and we break it all down. And what it comes down to is this right here, where the specific speed is N, that's the rotational speed of the pump, in RPMs. How fast is the pump rotating? N is RPMs, Q to the 1/2, and then the head that the pump adds to the 3/4, okay? So we can actually plug this in and then calculate the specific speed. And if we do that, then we can come back around over here. And and use this graph. Now, you need to be careful. Specific speed is usually calculated in the US system using cubic feet per second, and head is in feet. Okay, if I remember correctly, yeah, that looks like it. And so now noting here, okay, so here on this axis where my finger is at, we have the specific speed in US customary units. And then down here on this axis, we have it in the SI units. So let's say I had 2,000, I would come up here. First off, I would say I would come straight down to this part down here. So at 2,000, I'd come down and say, oh, I want a mixed type impeller. Okay. If I'm over here, say at maybe 20, or I guess I'll wait, not 20, that's 500, so we'd say about 700. Well, I'd want a pure radial flow. And here's the concept. We don't really use this to size pumps. We're going to get into pump curves, and that's where you actually use to size a pump. But this kind of tells you the type of the centrifugal pump to give you an idea of how it's going to behave. Radial flow pumps are really good for high head, low flow. So if you have to pump the water a long distance up, you're going to want a radial pump. If you need to do low head, high flow, you want a axial flow. Okay. And if you get farther into pumps, those have a little more specific meaning to them, but I think we need to delve into how we figure these pumps out, how they behave first before we go too much farther. So simply by using this equation here, we can calculate then, put in the let me scoot this back up. There's an example down here at the bottom of your book. So stick in the rotational speed, which is 1,450 revolutions per minute. In this case, it has a flow of 0.02 cubic meters per second. And we know we're pumping against a head of 25 meters. And then that gives us then our specific speed. We'd take that 18 back up here and come back up the graph. Would say 820 is going to be right here. So we're still in the radial flow area. All right. So that's how we can determine what type of centrifugal pump we're going to use. Now, let's talk about characteristics. But before we do that, we want to define what's called a system curve. And a system curve would be defined as how the system operates. And right now, for now, we're going to use a single pipeline. We're going to go back to basics, single pipe, okay? So, a little example here, if you will. If I have a reservoir down here, and it's connected to a pump, and it pumps now over so far, and then goes up a hill, and fills some reservoir up on top of this hill. We can look at this as Z sub 2, and over here is Z sub 1. So if I write my standard energy equation, okay, write the standard energy equation as P sub 1 over gamma plus Z sub 1 plus V sub 1 squared over 2G. Now I know I have a pump in there, and the pump's going to add energy, so I'm going to say plus the head of the pump, H sub P. And you got to be careful, we also use H sub P for horsepower, or HP for horsepower, not necessarily H sub P, but HP for horsepower. But this means head of the pump in this scenario, all right? That then is going to equal to P sub 2 over gamma plus Z sub 2 plus V sub 2 squared over 2G plus the head loss, which we have now defined as CQ squared. We've simplified friction times length over diameter. We've simplified all that, made it easier. Okay. So note that if I take this, P sub 1 goes to 0, P sub 2 goes to 0, V sub 1 goes to 0, and V sub 2 goes to 0. Okay. And we're going to define something then as the total dynamic head, or TDH, total dynamic head, is equal to the horsepower that's required for this system, H sub P, which now is equal to Z sub 2 minus Z sub 1 plus CQ squared. Okay. Any questions on that? So now I can actually make one other change to this. The total dynamic head, the TDH, is equal to delta Z plus CQ squared. Okay. This is the system curve. Right there is the system curve. Tells us how the system behaves. All right, let's look at the equation a little bit. Before I can even get one drop of water to move in this system, I have to lift it up this distance, delta Z. I have to impart enough energy to lift it up to delta Z. So if my pump only has the ability to lift the fluid up 40 feet, and my difference in my reservoir is 50 feet, how much flow am I going to get? Absolutely none, right? Absolutely none. But once I get flow moving, once I get a pump that will send it that high, as soon as I get it moving, now I have friction to overcome as well. So my pump has to overcome both friction and that delta Z. And the more flow I push through my system, what happens to the friction? The more flow I push through my system, the higher the velocity, therefore, the higher the friction, right? So we have this balancing act where I can push less flow and have less flow, less friction, but if I try to push more flow, then my friction goes up. And so the question is where's my system going to operate? Okay, so the system curve defines where the system is going to operate within, and I have to balance the amount of energy the pump is adding. I have to make sure that it overcomes the basic change in elevation, and then I have to make sure it overcomes the friction loss in my system. Okay, so now we can look at a pump curve. Now, a pump curve, this is for, once again, centrifugal pumps only. Okay. Rotational pumps. So if we go ahead and define then a standard Cartesian axis where we have flow on the bottom, Q, and head on the y-axis. Head is going to be defined as feet. Flow could be defined as cubic feet per second, cubic meters per second, but we generally do not do that in industry. When we buy a pump, it's based on gallons per minute, or a lot of times liters per second. Now, you got to be careful in the metric system. Sometimes it may be liters per minute. Sometimes it may be cubic feet, or I'm sorry, cubic meters per second. I think we go back to figure 11.2, where we talk about that. Yeah. I'll throw it back up here. They've shown it here in liters per second, gallons per minute, which is the industry standard. Okay. Now, why we do that? That's so you can make more money, right? You understand it, and the common person doesn't. But I'm half kidding there, but I'm half serious. All right. So a pump curve then defines the operation of the pump. So pump operation parameters. Let's say it that way. The pump curve defines the pump operation parameters. Okay. So a typical pump curve looks something like this. So typical pump curve. The curve concept, pump curve, tells you that it's not linear necessarily. Now there are some pumps that behave close to being linear, but not all. And most of them have a little bit of curvature going on. Okay. We have also, so this curve then defines the relationship between flow and head. A pump can provide more flow if it has to be at less head. So if I'm pumping against this head right here, I can provide this flow. So this H sub 1 is correlated to Q sub 1, right? I also have a point up here, I'm going to highlight, we're going to call this H sub naught. I'll come down here and say H sub naught is defined as the shutoff head. This means that if the pump is pumping up against a valve that is shut, it's pumping up against a dead line, there's nowhere for the water to go, it will add this amount of head to the system, but there's nowhere for that water to go. And pumping against shutoff head is not good for pumps. They tend to cavitate, it tends to ruin them. So you don't want to do it for very long. If you did it for just a little bit, it's no big deal. But long-term operation, if your system has your pumping against shutoff head, you're going to be buying a lot of pumps. Okay. But nonetheless, this defines then kind of the head that is added when there is no flow. Okay. And some pump curves actually have a little curve to them, so it's not always the highest head, but it's usually close, if not the highest. Once again, there could be a little bump right here since it is a curve. All right. Now that we have the shutoff head, we have the operation curve of the pump. We can now, well, there's also some other curves, or there's some other way of defining the efficiency of the pump. And usually this is with contour lines, but it could be defined with another curve. Okay, so these curves right here represent then, I'm going to bring this down over here, the pump efficiency. Let's see, probably misspelled that, but how efficient is our pump? How efficient is it of adding power to our water system? Are we losing half of our power to operate this pump and the other half makes it to the water? Or does 80% go to the water and 20% go to the pump? Every mechanical device has some amount of inefficiencies, whether it's friction, loss to heat, whatever, they all occur, but these pump curves then define the efficiency, all right? And there's going to be, at the highest efficiency right there, we call that BOP. The BOP is defined as the best operational point. Which is the highest efficiency. Now, if I overlay my pump, let me flip this around. If I overlay my system curve onto my pump curve, so let's say now we want to add system curve. Okay, so remember the system curve, the total dynamic head is equal to delta Z plus CQ squared. So immediately I have some delta Z on my figure that I have to jump up to. So I'll come over here, and this right here then represents delta Z. I have to at least add that amount of energy before I get one drop to flow in my system. And now I'm going to plot my pump curve. I'm sorry, I'm going to plot my system curve onto my pump curve. This then is my system curve. The intersection of pump and system curves is the operational point. So, let me go up there on my graph and we'll highlight that right up there. And that becomes then the operation point. Operation. That's how much is now flowing in my system. So if I have a system that has a valve at the end of it, so I'm pumping water from one pond up to another pond up on top of a hill, and I have a valve in my system, and I crank my valve down, what's going to happen to my flow rate? It's going to go down. What's the mechanics of it going down? What's the math behind it going down? How do we account for the flow rate going down when we turn that valve down?
You're increasing the K, the resistance in the fitting.
Okay, you keep going, Scott.
And that, of course, is increasing the head loss in the system, and that decreases the flow rate.
Good, so good. For those online, if you didn't hear that, by turning the valve down, we're going to increase our minor loss coefficient, the K, which then is going to, did I say, yeah, increase, we're going to increase it, which now is going to change our C value, which is going to increase the amount of minor loss in our total system. And mathematically, then that gives us more head loss overall. On the figure, how does that work? If I change the C value and make it bigger, my curve is going to be more sharp. So my curve is going to come up here. So this right here is increase in losses. And now I've just changed my operation point. So now I have less flow pushing up against a higher head because I'm burning that head up in my valve. And likewise, if I start open the valve, now that curve changes, right? So I can now find where if I take a pump and stick it in a system, and if I know the curve for that pump, I can now define where my system is going to operate. Right there, I just had it here. Okay, so here's a simple pump curve, but it doesn't have the efficiencies on it. Let me grab this one here. This one does. Do this one instead. Now this one doesn't have very much curve to it. That's okay because some of them don't. Okay, so let's talk about back in the day, before the internet, which was not too long ago, by the way. You guys, well, it's always been here since you were born, huh? But it hasn't been around that long. We didn't have access to this on the internet, so pump companies would send out these big old binders, like a 3 to 5 inch binder. And when you needed to find a pump, you would pick a particular company, you'd start looking, and there's ways to narrow it down. It's not like you'd go through every page, and I'll show you how you can narrow it down. And you'd get the pump. Okay, so this particular pump is a wastewater pump, and this is the performance, the pump curve, okay? And the model is C3355. It has an impeller code of 610. And you come down here and you'll notice that there's multiple lines, but this follows the standard procedure. But on the bottom, we have the flow in gallons per minute. On the x-axis, on the y-axis, we have the head in feet. And then we have these different pump curves coming down. Now, these little numbers, 420, 410, 395, and 380, I'll talk about those in a minute. But here we have these other numbers, 79, 77, 72, and so forth. These are the efficiencies, all right? Now, if I have a pump, let's say that I put a random, and this line kind of goes dashed because they say if you're going to do this much right here, you need the 148 horsepower motor. But if you're not there, there's another motor you can use. But if I just come over here and draw and say this is my system curve right there, then, and if I was using the 410 impeller code, then I would be operating right here, and I would be pushing about 74 feet ahead in my system at 6,000 gallons per minute, and my efficiency would be 79%. Now it may be a little bit, it may be 80 or so, but I can't say that. All I can do in between those is say 79. If they had a little plus symbol in here with 80, I could guess a little bit, but so my pump is going to operate at 79% efficiency. Okay, but my whole system then is going to be 6,000 gallons per minute at 74 feet ahead. Any questions on that? All right, let's talk about these curves up here. Okay, these curves up here then represent what we call trimmed impellers. So a pump has the casing, that's the outside of the pump, and the inside we have an impeller. And sometimes that impeller is usually designed to be very tight fitting. There's very small tolerances between the pump casing and the impeller. Sometimes there's a little bit bigger holes between them, if you will. Wastewater pumps sometimes have, the way they're designed to pass kind of large solids. In fact, one pump company wanted to see if they could pass golf balls through their pump. So they did, and it worked. So you can also come in and do what's called trim the impeller. So you're going to use the same model of pump. You're just going to like pull out the impeller and stick a different one in. And it's usually a smaller one, which gives you a little bigger gap there, which actually decreases the performance, but there are reasons for this sometimes, okay? So for example, if I had decided to use the 380 impeller with my system, I would be down at 72%, but my flow would be closer to the 4,800 gallons per minute at a lower head, okay? Now, if I'm always throttling my system because it provides too much flow, it may be to my advantage to trim the impeller, all right? Now, I would note that there is a variation to this, and it wasn't that popular. It has existed for years, but it's only gotten popular, I'd say, in the last 10 years, of what's called a variable speed drive, a variable frequency drive. What we do is, due to electronics getting better, now we can change the rotational speed of the pump. And rather than changing the impeller, we're going to slow the pump down, which is going to change the performance of the pump. So we'll talk about variable speed drives in another lecture. But understand there's a couple ways of changing your pump. You can change it either by trimming the impeller or slowing the rotation down. Okay. All right. Why is the efficiency important? So we talked a little bit in this class, I believe, about power, correct? I'm trying to think, when did we talk about power? I remember going through it, I think. Did we or did we not? Or maybe I'm mixing it up. I'll have to go back and look at my notes. But power, then, in a pump, P is equal to gamma QH, where gamma is the specific weight, Q is the flow rate, and H is the head. This is the amount of power, okay? Now, we could derive this equation. It's not that hard to derive because force is equal to power times, work is force times distance. Power is force times distance per time. And we can actually then take the force. The force is going to be the specific weight of the water times the volume of water. That's where the time comes in. And we kind of break everything up and we end up in the gamma QH, okay? But power in terms of horsepower is equal to gamma QH divided by 550, okay? So this right here is the general equation. It doesn't matter what system you're using. It's going to give you foot-pounds per second, or it's going to give you joules per second, okay? Which is, by the way, watts, right? Now, if we want it in terms of horsepower, because in the English system, that's what we use to define power a lot, is horsepower. So there's 550 foot-pounds per second in 1 horsepower. So divided by 550 now gives us the power in horsepower. If we want power in kilowatts, then it is gamma QH divided by 1,000 because there's 1,000 watts in 1 kilowatt. So this terms in units, I should say, unit-wise, then this goes to kilowatts. Unit-wise, this goes to horsepower. Okay. Now, an interesting thing is that we rate our pumps based on the motor, but then we also sell electricity in kilowatts or kilowatt hours. So it's like we have to always do this conversion. But before we go there, note that a pump has an inefficiency. So if this is what we call the water power, P, so water power, water horsepower, that's equal to gamma QH divided by 550 times the efficiency of the pump. No, I'm sorry. Well, that is correct. Is that correct? Okay. This is the brake horsepower. Sorry, that's not the water horsepower. The brake horsepower. This right here is the water horsepower. That's the amount of energy that's going into the water. Okay? But in order to get that amount of water to go, that amount of energy to go into the water, we have to provide a certain amount of energy to the pump. And that's where the efficiency of the pump comes in, where E sub P then is the efficiency of the pump.
And is that taken as a percent or a decimal?
Decimal. That's a good question. Because it just reduces it. Okay? Or in this case, it actually increases it because if you divide this by something that's less than 1, it's going to increase this number, which means if I'm providing so much brake horsepower to my system, I have to provide water horsepower to my system, I have to provide a certain amount of brake horsepower to my pump. Okay? Then we also have the efficiency of the motor. E sub m equals the efficiency of the motor. A lot of people don't realize this, that pumps and motors are separate. Excuse me. If you go down to Lowe's or Home Depot and you buy a small little submersible pump, they look the same because they're combined. They're in one unit. But in reality, you have a motor and then it has a shaft and it goes to the pump. Okay? So the pump has an inefficiency, the motor has an efficiency. Now, we're not going to get into electrical rating of motors. You can generally get that from the manufacturer, but this is generally around 75 to 80%. Motors are pretty good. Okay, maybe 82. Some really high efficiency motors may go a little higher. But if we want to know the total power going to the motor, how much electricity do I have to provide to the motor? Then, so P total is equal to gamma QH divided by the efficiency of the pump divided by the efficiency of the motor. Now, I haven't done any conversion here to horsepower or kilowatts yet. So, I mean, this applies the same thing. If I were using the English system, this would give me the total amount of power in pound-feet per second. And this would be the total amount of power in watts for the metric system. So if I want it in terms of horsepower, I divide by 550. If I want it in terms of kilowatts, and I'm using the SI system, I divide by 1,000. But if I'm doing work in the English system, gallons per minute and so forth, which I have to convert to cubic feet per second, by the way, and I want to turn it into the power for electricity to calculate how much electricity my pump's using, I'm going to have to do the conversion from feet and cubic feet per second over to kilowatts. And we don't have time today to go through that conversion. Ends up being a single number, but I want to spend a little more time because they've done some screwy stuff in industry with it. And I want to show you why you can use, there's two numbers you can use. I want to show you why you can use either one and still be correct. Okay. So with that, any questions about power and pumps, pump curves, system curves? You should be able to now go ahead and calculate the system curve. You already have that ability with the Bernoulli, with the energy equation. And then if you are given a pump curve, such as this right here, you should be able to plot the system curve on top of the pump curve. Now, how many points does it take to plot a curve? How many points to plot a line? 2. So a curve? 3, right? To do a reasonable approximation of a curve, you need at least 3 points. So one of those points, you can say, what is the delta Z? You pick a point out here, pick another point out here, and draw a curve in. So if you're given a pump curve, you can draw a system curve on top of it, and where they intersect is going to give you the operational point of that system. Okay? Now, on Monday, we'll go through a full example. I'm going to assign you one problem from the book to deal with the specific speed. It's fairly simple. I may give you a problem on this to kind of at least get started on this, and then we're going to build on this. We will work an example on Monday, and also then talk about power and build on this to keep going with pumps. So with that, if there's no other questions, have a great weekend.